Kent seminar lecture. Today we have the privilege of having Dan with us. He has a PhD in structural engineering. He did his undergrad in Virginia Tech, and he did his master's and PhD in the University of Illinois at Urbana-Champaign. He is currently he works with a lot of he manages a lot of projects for IDOT. He is a licensed professional and a licensed structural engineer. Some of the projects that he is managing are custom placed, precast and pre-stressed concrete, roadway geotechnical, metals and miscellaneous, bridge investigations, experimental features, and material testing laboratory certification. And today he's gonna give us a very nice presentation about the overview of seismic bridge design philosophy in Illinois. Dan, the floor is yours.
Thank you so much. Okay, I've got about 55 slides, so I'm going to talk kind of fast for the group. My topic today, as you can see on your screen, is overview of seismic bridge design philosophy in Illinois. And so I'm going to kind of try and give you guys sort of a short history lesson of what's been going on in Illinois for about the last 20 or 30 years or so, but as well as also in the last number of years, many years on the national scene, and how these two topics are kind of intertwined. Okay, so first we'll start off with a little introduction, a little history, and we'll talk about modern developments in seismic bridge design, development of what we call our initial IDOT ERS strategy. That means Illinois Department of Transportation Earthquake Resisting System Strategy. Okay, all states, generally speaking, who are in kind of earthquake zones, which Illinois is, we are supposed to have something like that, or we're instructed to have something like that. Okay, and I'm going to talk a little bit about development of modern AASHTO guide specifications and code. This has been going on now for about the last 20 years or so, and it's still ongoing, actually. And then I'll talk about the concurrency of how IDOT has evolved along with AASHTO. And then at the end, I'll talk about some research that we had the University of Illinois at Urbana-Champaign do to help us refine our IDOT earthquake resisting system strategy. Okay, so just like the history of earthquake engineering in 1 minute here, okay, now it's really become kind of a much more important subject since around the 60s and 1970s, but probably more around like the 1950s. And it really kind of coincides with as civil engineering and structural engineering in particular got more sophisticated over the years, beginning in the early 1900s, when codes were starting to get developed, building codes and things like that. And we were getting more sophisticated. Our science was much better. Our engineering got much better. It took around to the 40s, 50s, something like that, for us to really start paying attention and learn how to design structures for earthquakes. Now, you would expect that California and Alaska and some other Western states that really have a lot more earthquakes than we do here in the Midwest or even on the East Coast, they've really been ahead of the game, okay? And so they've been kind of the front runners for many, many years, and they still are to a large extent. Now, since around the 1980s and the 1990s, there has also been a growing and heightened awareness of the seismic risks, to other parts of the U.S., okay? So once California kind of got a foothold and Alaska kind of got a foothold, then we started paying attention to other regions of the country that we've known historically have had earthquakes, but they just don't happen as often. And of course, our area here is one of them. We're in what's called the New Madrid region. Okay, so around this time, so this would have been about 30 years ago, we really started paying more attention to earthquakes in other parts of the United States besides the Western states. So large earthquakes are known to have occurred in what we call the New Madrid Fault region, and also very large earthquakes near Charleston, South Carolina. And what you can see, and I won't focus too much on the map that's on my right, that's talking about the MMI intensity. That means modified Mercalli intensity, okay? because a lot of that shows just a whole bunch of earthquakes with magnitude 5 or greater. A lot of those are pretty small earthquakes. 5 is really not that big. But you can see there's a lot of earthquakes on the West Coast, actually a fair amount on the East Coast. But the really big ones on the left side of your screen, those have really come from the New Madrid Fault. And because of the geology of our region, the earthquakes in the New Madrid Fault are felt for many, many hundreds of miles as compared to the California earthquakes. Those are very large earthquakes as well, historically speaking, but they don't travel as far because the geology is different. They have mountains and things to stop the earthquake. But a lot of people don't know this, but South Carolina, especially near Charleston, that's a big earthquake hotbed, and they've had very large earthquakes along with along the New Madrid Fault. Okay, so as I kind of started to mention before, California really has led the way in the development of what I would call seismic design criteria for bridges in the United States, and it's still largely true today, but not completely true. Now, in the early 1980s, so as far as earthquake engineering goes, that's a pretty long time ago, okay? And earthquake engineering developments happened very quickly, okay? They've been happening very quickly for about the last 40 years or so, okay? And so California started it off, and then AASHTO kind of got on board. And then in the early 1980s, and what we used to call the old bridge code was called the AASHTO standard specifications. That had some seismic design provisions, which are like code provisions, which are like laws, okay, for how you design things. And those were probably largely came out of California, okay, or California's experience, I would say. And then around this time too, there are other specifications that AASHTO publishes that are called guide specifications. And those are specifications that can have the weight of law, but states and designers don't necessarily have to use them if they don't want to. Okay, so in the 1980s, there was laws you had to do that weren't super rigorous, but there was also a guide specification that was much more complete as far as seismic provisions are concerned. And at that time, in the 80s, that was a guide specification. But something happened in 1989, okay? Because these new guide specifications that were developed in the 80s, this more rigorous guide specifications, they were almost instantaneously, in a very short period of time, promoted into the code, into what's called Division 1A of the code. And why was that? Well, for those of you who are old enough to remember this, which may not be very many of you, but I remember this, okay, 1989 was my first year in graduate school, okay? Well, during the World Series that was happening in San Francisco and Oakland at that time, two cities that are very close to each other in California, right before a World Series game was supposed to start, there was a big earthquake. And so, you know, and at that time, their cable TV wasn't very prevalent. There was no cell phones or anything like that. So the number of people watching this game was probably many millions more than would be watching it today, because there's, you know, today there's a lot more options for people to watch TV and stuff. So this had a huge impact on the whole United States, where it made people much more aware of the devastation that earthquake causes. And of course, this is a very classic picture from one of the bridges, that a double-decker bridge they call it. It's like a viaduct double-decker bridge that collapsed. I think this one was in Oakland, that a number of people were killed and stuff like that. So it caused, that earthquake caused a lot of reverberations politically and engineering-wise across the United States. Now, for right now, I'm going to just get a little tangent here, okay, because seismic design strategies and code provisions and criteria, they're kind of treated a little differently than regular code provisions for design building codes. A lot of times criteria happens before codes, and the criteria are kind of like rules and policies that states or municipalities use to do design. And they're usually interpretations of code, okay? And because seismic happens so quickly, the evolution of it happens so quickly, the codification, the lawmaking of seismic provisions, a lot of times is behind the actual evolution of design criteria. It's usually the reverse. So when you hear me talking about design criteria, I'm talking about stuff that isn't necessarily law, but when you hear me talk about the code or the guide specifications, those generally are law. So if you're confused about some of the terminology I'm using, I just want to kind of make you aware of that. Okay, so around 1990, 1991, those guide specifications, those more rigorous guide specifications, they were promoted to actual law. Okay, so it's kind of guide specifications are sort of soft law to hard law, where you had to follow them. Okay, everybody in the United States had to follow them. Okay, and these were the first design provisions, seismic design provisions that I ever learned of. And so that would have been, 30 years ago, 31 years ago. Okay, and it turns out that the return period for the design earthquake for these specifications was, quote unquote, only 500 years. So for those of you in civil engineering and are not structural engineers, the equivalent of that is like if you're designing for floods and you're designing a drainage system, you would design a lot of times for what you would say is a 100-year flood, the largest amount of water that you would expect every 100 years. Well, for earthquakes, what this meant was for 500 years, you would be designing for the largest earthquake you would expect in your region where your bridge is, that would come about once every 500 years, okay? And that really actually equates to probabilities, which means a probability of exceedance once in every 50 years. And looking back 30 years ago, the methods that were in this code, they were what I call foundational. They're real basic bread and butter seismic design principles that are still used to this day. And but don't get me wrong, I mean, they're still very useful, but there are some methods that are a lot more sophisticated than they used to be. But at this time in the early 90s, and all the way even through the 90s, for Illinois, this was very radically new to us, okay? There was not very many folks practicing structural engineers who really knew anything about structural dynamics, much less how to design any buildings or bridges or any structures for seismic loading. So it was kind of a big shock to us. But for folks, engineers on the West Coast in California and in Alaska, Washington State, it wasn't very new to them, but it was for us. So we were really behind the learning curve on this one here. Okay, so that's why I say we kind of had to play catch up, okay, to what I'm using the baseball analogy here of the Major League West Coast. And during the 90s, really a state like Illinois, as far as expertise is concerned, we were just trying to make it to AA ball. Okay, so like I mentioned, this Loma Prieta earthquake, it got the people's attention. And I remember I worked for the state bridge engineer in the early 2000s, and he told me stories about how after the Loma Prieta earthquake, he had to go testify in front of the Illinois state legislature, and he had just been appointed to the state bridge engineer's post, and it was quite an ordeal. And even around this time too, where when this became law, if you want to become a structural engineer, a licensed structural engineer in Illinois, right around this time, they started putting seismic design requirements. You had to have expertise in seismic principles of design in order to pass the exam. And even to this day, that's the part of the exam that still most people fail. Okay, and it's not a small percentage. I mean, it's not like 2 or 3%. It's like 30 or 40% of the people fail. So we're still kind of working on getting expertise in our state and others. It's kind of an involved subject. So now if we move into the 1990s, as the guide specs became the code, Illinois was kind of like, well, I guess we need to do something. We need to come up with some criteria of our own based upon the code of how we're going to, it's kind of like interpretation of law of how we're going to implement the code. And to be truthful, Illinois didn't really do that great of a job in the 1990s. We were kind of loose in what I say, not coalesced criteria. And if we did need some expertise in doing some designs on critical routes, critical bridges, then we could hire. There were some people who did have good seismic expertise, and we could hire those consultants to do seismic retrofits for us. But on the flip side of that too, in Illinois, a 500-year design return period, the seismic demand or the accelerations that we were required to design for, they really weren't that high unless you were really down near the very far southern tip of our state, near a town called Cairo, Illinois. Okay, so we had to learn seismic in Illinois in the 1990s, but we didn't have to learn it near as well as the folks in California had to know it. So I kind of call that California light, okay? And this is just an example of some of the bridges that were retrofitted during the 1990s down near East St. Louis. This is of course, across the river from St. Louis. And there's a whole series of bridges where interstates converge there that have a lot of what we call flyover ramps and things like that. And these were all retrofitted a number of years ago. Cost us, I can't remember, it's like $120 million, something like that, to have these things retrofitted. Okay, now by the time the original guide specs were put into the code in the 1990s, it's like I said, AASHTO and the national researchers and earthquake engineers and all these types of folks, they were already planning for the next version, the next update to the design code already, okay, while like Illinois and other states were trying to catch up, okay? And so they were thinking about things like increased design acceleration, improved what are called design response spectra and soil coefficients. Part of what that really means is that an earthquake might happen far underground, and how much the seismic waves are amplified as they travel through the soil has a lot to do with what the soil type is, okay? And that's a very complex geological sort of relationship to kind of come up with. And the original soil coefficients for this, they really weren't very good, and so they were working on more sophisticated methods to figure out how much amplification there was based upon the type of soil that you had. And then there was a whole new type of design method was also being developed called displacement-based design, which a lot of people call pushover. The older style design method was called R-factor design, okay? And the easy way to term that is called force-based. So there's force-based versus displacement-based. And the easiest way to describe the two without getting into any detail at all is that displacement-based is a very theoretically accurate way to do seismic design, and R-factor is sort of like an approximation of displacement-based. Okay. But of course, it would not be until around the early 2000s before anything new got adopted. Okay, so in the early 2000s, the Federal Highway Administration and academia put a lot of pressure on AASHTO to start to modernize. They said, hey, you've got 10 more years of research and development. It's time to move forward and to incorporate modern methods. And so there's a lot more politics that I don't have really a lot of time to get into in our lecture today, but it's very political. If you don't think that there's science and politics or anything like that, it's just like what's going on today with the pandemic and the coronavirus and everything. And you see stuff in the news and you see Democrats say things and Republicans say things and all this stuff. If you think that they're just talking about the good of the public and the good of science and all of that sort of stuff, that's just very, very naive. There's politics even in a public health scare, okay? And just like there's politics in a public health scare, there's politics in earthquake engineering. Trust me on this one. I've lived this for many years, okay? And it's very, very similar. Anyway, so one of the big fights had to do with what should we do for new design accelerations? And there was talk of having a much higher design return period from 500 to 2,500 years, or maybe 1,000 years, or maybe 1,500 years, or maybe we should have two different levels of design earthquake, 100 years and 2,500 years, and there's a lot of talk about that. And part of what happened along the way was that, and this gets into some of the politics, a couple of years before in the building industry, the academic folks especially, these were people who were like in New York State of all places and California, they were really pushing for a 2,500 year design return period, which meant that the seismic demand you would have to design for the accelerations would be really high, okay? And that would mean that buildings would be a lot more expensive. Well, it turns out that those building folks, the folks that wanted that, they were defeated, and they were very, very angry about that, okay? Because what actually made it into the building codes was not 2,500 year return period, but what we used to term as 2/3 times 2,500. And in probability terms, 2/3 times 2,500 year return period, that really kind of equals 1,000 years. And it has to do with probabilities about why that is. So they didn't get what they wanted. And so when they didn't get it with buildings, they were trying to get it with the bridges. Okay. Now, so, oops, I went the wrong way here. So let me go back just a little bit here. Okay. So Illinois knew that something was coming. It probably wouldn't be 2,500 year return period, but we know it would probably be at least twice that much. So when the design accelerations in Illinois, when we knew they were going to go up, we knew we had to really develop our own criteria that was much more robust than what we had been doing in the 1990s. Okay, so as I write in our presentation here, the handwriting was on the wall. It means we have to do something. So we were fighting our political fight to try and get a reasonable new design accelerations that weren't too large, and at the same time we were starting to formulate our own plan. Okay. Now, very generally speaking, California's seismic design criteria, and really even the early codes and guide specifications, those were really tailored towards California bridge types. Okay, and California has a lot of what are called post-tension structures with single column piers. Okay, and Illinois doesn't have hardly any structures like that at all, actually, especially in earthquake-prone regions. Okay, and a lot of Illinois' bridges, they're just steel or pre-stressed concrete girders with a concrete deck, and then elastomeric bearings and several different kind of varying pier types. And the piers can also be quite short because, of course, we live in the prairie state. Okay, so this is probably an overly dramatic and biased picture, but there is an example of a California bridge that failed. Okay, and these types of bridges that are in California, we don't have very many of these, but we have a lot of these type bridges in Illinois that are just reinforced concrete deck with pre-stressed beams or steel beams and wall piers or multi-column bents, we call them. And so these two bridge types behave fundamentally different. So what we decided to do was to tailor our criteria to our bridge types, just like California tailored their bridge design criteria to their bridge types. Okay, and of course that's what we did. So what we decided to do was take advantage of what we would call a weak link, okay? And our weak link, which is actually a good thing in this case, was the connection between our superstructures and our substructures. And the connection between our superstructures and our substructures are what we call our bearings, okay? And so these are really our support conditions. So our bearings really approximate like a pinned connection or a fixed connection. And when we talk about a fixed connection in a bridge, a fixed connection is not what you typically think of from what you've learned in school from like basic structural analysis. We think of a fixed connection as being able to rotate, but it can't move sideways back and forth, okay? And a pin connection is a pin connection. It can rotate, it can move back and forth. And so a connection like this, these elastomeric bearings, these are as close as we can get to a pin connection. And these things are made, if you look here, if you can see my pointer here, these are made with layers of rubber with that are either natural or synthetic with tiny little steel plates in between. So they're very, very flexible, okay? And so they go back and forth. And so what kind of happens with these is that because they have that nature, okay, when an earthquake comes, when the earth shakes, okay, they tend to isolate some of the earthquake motion between the piers and the deck itself. Okay, so not as much of the full design acceleration because of the types of bearings we have go fully into the deck. Okay, and that's a very good thing. It's not full isolation, okay, but we call it semi or quasi isolation. We also call it sacrificial fusing. So we didn't even care if the bearings broke or not during a big earthquake. If the bearings broke, and that was all that broke on the bridge, and nothing happened to the piers and nothing happened to the deck, we'd be very happy with that, because it's much less expensive to just replace the bearings than it is to replace columns and piers or superstructures, which would be, with the superstructures, the deck. Okay, so this fusing, we call this fusing between the connection between the deck and the substructures, that does absorb seismic energy, and it also changes the period of the structure itself. It lengthens the period. And if you don't know very much about structural dynamics and earthquake engineering, if the period of your structure goes up, that means that the response of your structure will be less. Okay, and that you have to know a lot about structural dynamics and earthquake engineering to fully understand that. Okay, so our earthquake resisting system strategy was built around this concept of fusing and levels of what I call seismic structural redundancy. And we have 3 levels. One is the fusing of the bearings, and then the other one was, if the bearings broke, then we wanted our piers and our abutments to be wide enough that the bridge deck could slide around. Okay, so and there actually are rules in the code about how big your piers and abutments have to be. Okay, just in case they break. But for our system, they had to be even bigger than the code required, just in case our bearings broke. And then we also used the traditional 3rd level, which would be a fusing, if you want to call it that, which is plastic hinging of our substructure elements, which is columns and walls, etc. And that's very classic earthquake engineering. So we kind of have 3 levels of what I would call redundancy, which is a great thing. Okay, and so the weakest level is the weakest fuse is level 1. That's where we want it to break, and the strongest is level 3, where if that doesn't happen, that's a good thing. But if we need that seismic capacity, we have it. Okay, so in a very basic sense, then, IDOT's earthquake resisting strategy is unconventional and conventional at the same time. The fusing part is fairly unconventional and new. It's fairly unique in the United States, but not completely. I know that Taiwan out in the Far East, they are very interested in this concept and take advantage of it. I think Japan has started to as well. Okay, and then the conventional part is the seat widths on your piers and your abutments, and then the plastic hinging detail. So as part of developing our strategy, we had to come up with some typical details for designers to use. And these are things that, if you know about earthquake engineering, these are very common types of details, where when you have your longitudinal steel in your columns, where you're supposed to splice, and you're supposed to also have confinement reinforcement in your columns. And that's all these kind of drawings are, showing different ways to achieve this type of reinforcement in different pier types. So this would be like for what we would call multi-column vents or multi-column piers. And this would be for what we call drilled shaft piers. And there's several variations of drilled shaft piers, okay? And if you can see my cursor here. So right below these mechanical splices, that's where we would plan on having, in this kind of region here, that's where we were planning on having our plastic hinges. We also have kind of an odd pier type, which has trapezoidal piers. And so we have special details for those, for the confinement reinforcement and for the longitudinal reinforcement. And then there's also, these are also very common in seismic design, these seismic hoops. There's nothing unconventional about these. These are used, these types of designs for shear reinforcement for columns, they're used all over the world. So we did a lot of work, you know, while there was a bunch of political fights going on about what the new design code was going to look like. And so we were doing all that background work, getting prepped for the new design code. So we felt pretty good about that. And it was kind of interesting. I mean, and I was really directly involved in this the whole time as a representative from the state of Illinois. So it was kind of like a civil war. It was sort of like a civil war between primarily the state of Tennessee and Illinois, maybe a little bit. South Carolina, oddly enough, was a little neutral, but we were Tennessee and Illinois were kind of at war with California, Alaska, and Washington State, generally speaking. And it kind of was a civil war, and it was very political. Okay, and that fight, and it was very acrimonious too, and that went on for like 5 years. Okay, so if you compare that to the, since President Trump was elected and how much political fear has gone on since he was elected, that's only been going on for 3 or 4 years. We fought about design accelerations for 5 years, if you can imagine. So in the end, we agreed to have a 1,000-year design return period. Okay, and what that really meant for us, because there was also new soil coefficients, is 500 to 1,000 didn't mean necessarily that our design accelerations were twice as much. Sometimes it meant that they were twice as much, and sometimes it meant that they were more than 2.5 to maybe even 3 times as much. So it depended on what type of soil you had. So this was a really, really significant increase for us. Okay, and then the next fight was over design philosophy. Okay, so for Illinois, for a lot of our state, okay, and I'll try and summarize this really quickly. For a lot of our state, we felt like it was still okay to use kind of the approximate method or the R factor method, and for a large portions of our state, okay, because really the design accelerations weren't as high a lot of times as California. And California only seems to, and Alaska and states like that, they only seem to focus on the highest of the high design accelerations. And that's where displacement-based or pushover is really the most useful for. And so they were very, very concentrated on that, where Illinois is concentrated on using displacement-based design in far southern Illinois. But as you get further north, we felt like R factor was okay. And so we were kind of fighting that. We wanted that option. And so we were fighting about that. And in the end, the way it worked out was Illinois turns out to be much better code writers. So I was one of the main people that wrote the code, I guess you might say, for the design code. And the Western states were kind of trying to have somebody else write their own guide specification, and they were having a lot of trouble. So once they saw that we could write a code and they were having a lot of troubles, then we kind of got what we wanted, because when the end, what happened was I helped them write their own guide specifications for displacement based, and at the same time then, so we kind of made a deal. So they got what they wanted, we got what we wanted, and I helped them write their code, and so we got 2 different design methods are essentially codified by law. And the guide specifications, these ones are very unusual because there's a clause in the design code that says that those seismic guide specifications that use displacement base can have the full force of law. So it's a little bit of an unusual case. Okay, so my short way of saying that in this slide is we smoked the peace pipe. That's what I call that. Okay, and really what happened too was in the end, the guide specifications that use displacement base, they actually turned out a lot better because they got much better refined for lower design categories, for lower design accelerations, which was really sorely needed in those guide specifications as well. And also, one of the things that we got our way in writing in the code was our concept of fusing, our bearings fusing and being sacrificial. So in the end, it all turned out really, really great. And so we fought for like 5 years, 6 years, something like that. And in the end, we were all friends after the war was over, and everybody got what they wanted, and everybody was happy. So it turned out really, really well for everybody. Okay, and this is just a picture of the front page of the guide specs that we came up with. And I did work on these like a lot. I put a lot of work into these. These are very, very interesting to write. Okay, so today's lecture is really meant to just be kind of informative. It's not meant to be, just kind of give you an idea of what's going on without getting very, very technical. But if you want to write me, I can send you a paper that I wrote about this. That's called, it was published by ASCE in one of their journals. And it's called Overview of Earthquake Resisting System Design and Retrofit Strategy in Bridges in Illinois. Or you can also go to Illinois' Bridge Manual, that talks about how we want our ERS strategy implemented, and we also have a guidebook that's like a bunch of examples with a narrative. It's sort of like a textbook for how to do seismic design in Illinois that I wrote a couple of years ago. Okay, so that was our first effort. And then after all that happened, and we got all that developed, we got our ERS strategy, we got it implemented, we got the new code, we got the new guide specification. We knew that we needed to do some research in order to refine our own method, okay? Because we really didn't understand very well exactly how our bearings would fuse. We needed to quantify it. So what we wound up doing, of course, is hiring the University of Illinois at Urbana-Champaign. Of course, I'm a proud alumni of U of I, and my advisor was Dr. Fouch, and he's been retired now for several years, but he was a major seismic expert there, along with a number of folks at the time there, and there's still a lot of seismic experts. And so I had him on the project and several other people, and we started doing some testing, and we wanted to, you know, what is the fuse-like behavior? We needed to quantify it, and we wanted to look at some other things like system performance and different abutment types. And we really did we spent $1.2 million on this research, which for the Department of Transportation, that's a lot of money. And we spent 10 years doing it, okay? And so there will be some changes coming out in our refinements to our strategy in our bridge manual and our seismic design guide in the next couple of years. But it turns out that AASHTO is in another cycle of coming up with some more design provisions. So we're kind of waiting to be in concert with them over the next year or two. So this will eventually come along over the next couple of years, and all the stuff that AASHTO is doing and working on, and the stuff that we've been working on. So it's sort of like a second iteration on both the local and the national level. So this is just a schematic here of one of the testing rigs that we had made up, that U of I made up down in Newmark Structural Engineering Laboratory to test bearings. And this picture should look very familiar. It looks just like the inside of the structural engineering laboratory there in Newmark, right? And they got the high crane bay and all that sort of stuff. And, you know, I spent many years there. It's very familiar to me. And so we were really, with that particular apparatus, these are the first tests we were running. We were really pushing these bearings, these rubber bearings, way past their conventional design limits for regular loads that were not earthquake loads. And to our knowledge, we think that these were the first types of tests on bearings like this, pushing them this far, that have probably ever been done in the world. If they weren't the first, they were one of the first. Okay, so this is very, very interesting testing. And of course, you can see we would get these typical kinds of responses where we measured the back and forth nature. And if you're familiar with earthquake engineering at all, you'll see plots like this a lot of times for columns and various things. And we would typically call plots like this hysteresis loops. But it really helps us characterize the bearings. We also have what are called side retainers next to the bearings. And so we kind of used a lot of force to what's called push those over. It's kind of hard to see, but in the back, there's an angle back there. Okay, so that's really what we were breaking. And the angle is bolted into the piers of the abutment. So we were testing how strong they were or what their pushover capacity was. Okay, and of course we get a lot of data, and of course those of you who are graduate students are very familiar with finite element modeling. It doesn't matter if you're a structural engineer, transportation, hydrology, or whatever it is. Of course, we always like to do a lot of computer models. We get a lot of data, and we try to extend what we know using computer models. So our researchers at U of I came up with a bunch of different kind of earthquake sort of traces that we thought would probably happen in Illinois over time. And we subjected all of those, bridges, computer bridges, finite element model bridges to these design accelerations and stuff, and saw how they behaved, and did a bunch of parametric studies, all that sort of stuff, right? And we learned a whole bunch of stuff, and I'll just talk about a couple things today, okay? we learned that our fuses can be a little bit too strong. They don't break up as quick as we want. So we weren't getting as much isolation as maybe we would like, okay? And a whole class of abutments called integral abutments, those put a little bit too much demand on the piles. I won't get too much into that, but we call that ductility demand. So we're kind of looking at how to reduce some of that ductility demand. There are some problems with unseating and skewed bridges. And another thing too that we found out is that in order to really implement a good design calculation strategy to fully utilize our quasi-isolation, we really actually have to go from R factor or force-based design to displacement-based. So that's really going to be a big deal for us when we do that over the next couple of years and actually teach structural engineers to do that across the state. Okay, so here's just a couple of slides showing, okay, well, maybe we can make the bearing slide a little bit more, or another strategy we could use is maybe we could make our columns and our abutments maybe a little bit stronger. So if we make those stronger, then that would enhance the fusing of the bearings, for example. Here's some strategies for taking some of the ductility demand off of the piles for integral abutment bridges, right? So the piles are right here. If you can see what I'm doing, I'm circling the pile here. So you make you put some coal tar on the back to increase friction there, to engage the soil in the back here, which is really a bunch of rocks, is really what it is. A bunch of aggregate is really what that is. So a couple little strategies there, and having more pipe restrainers or shear blocks to help for highly skewed bridges, so our bridges won't unseat just in case they fuse, things like that. But here, I'm almost done here. So in our bridge manual and our seismic design guide, this is where implementation is going to take a little while, because we actually have to develop simple methods that designers can use. So at the Department of Transportation, there's only about 2 people like me. There's me and another guy who are really pretty adept at seismic design. So part of what our job is in writing these manuals and design guides that have examples is we need to write in methods that are simple and straightforward, that designers that don't have as much expertise as us to actually perform these designs and perform them competently. So it's pretty tricky to develop those types of methods. Okay, so that's one of our big goals, because sort of one of our responsibilities over time has been to be kind of sort of like teachers to the rest of the practicing structural engineers across our state. So that's going to be kind of tricky. And to do this, we kind of have to do a kind of a hybrid of actual seismic isolation principles. Okay, so it's kind of like taking seismic isolation principles and adapting them to quasi-isolation. And I actually do know a fair amount of this. I've actually worked on this guide specification at the AASHTO one. It was pretty interesting. Okay, and so part of the easy methods for doing this would be, and some of you guys might not believe this, would be to take sort of like a regular bridge and not make it too complex. So there are methods for even bridges that have, say, 3 spans, a couple piers, a bunch of different stiffnesses that you have to consider, where you might not think about it, but a model like this for a bridge is really only a single degree of freedom structure. You can believe that. So there are ways to make complex problems simple, and that's what we try to do as much as we can, where appropriate, for regular bridges. For very complex bridges, like cable-stay bridges and things like that, we would hire people with a lot of expertise to do those very complex scenarios. But that's not really what typically goes into our bread and butter designs. Okay, that's all I've got for today. I'd be happy to entertain any questions from the group.
Thank you so much, Dan, for this very nice presentation. We can now open the floor for questions. So if you guys have any question, please go to participant and raise your hand. Then I do have a small question about especially like the last slide because it's interesting
Uh-huh.
about like the level of complexity in which we usually study stuff, and then at the end in the implementation the way that we need to make them as simple as possible. Like for example, I work in modeling, but sometimes whenever we want to go and then provide something to the public, we need to simplify it in a big way. And you
Absolutely.
were can you hear me?
No, no, you went out. I couldn't hear what the last part of what you were saying.
Yeah, so the question that I was asking, how do you decide between what are the projects that you can like you were talking about for specific projects you go and then you get the experts versus the other one you can just go with whatever specification that you already have. So
Right.
how
That's a
does
good question.
it happen?
So probably about 90 to 95% of all bridges are very simple bridges. So if you're just traveling around the interstate or around town in, let's say, Champaign-Urbana, a place like that, almost every single bridge that you go over, those are very simple, what we call garden variety bridges. Okay, and those can be designed for seismic loads. Okay, that you can do a seismic design for those with very simple methods. Okay, and those are actually 90 to 95% of all bridges in the world, all bridges in the United States. Okay, but once you start getting into bridges that, let's say, for example, are long span bridges, like let's say across the Mississippi River or the Illinois River, or that are like cable stay bridges or tied arch bridges, um, uh, even truss bridges, long span truss bridges. Truss bridges have very, if I can explain this, their dynamic response to seismic loadings, to accelerations, is very, very complex compared to bridges that just have regular piers that have a couple of columns and abutments and just a bridge deck and beams. If you just have bridge beams, a bridge deck, and just regular old pier columns or wall piers or things like that, we know that those are very, very simple, and those can be modeled very simply. And that's really what's shown on this slide here, is a bridge like that. But once you get to like a cable stay bridge, suspension bridge, tight arch tight bridge, even truss bridge, even long span truss bridges, once you get to those type bridges, those take a much higher level of expertise and much more and actual very complex modeling.
I see. Thank you so much. There is another question from one of the participants. Yes,
Okay.
you can unmute yourself and ask the question.
Yeah, I have one question about, does IDOT use any advanced material such as high damping material or some passive control strategy, or there is no need to use this?
We have experimented with such things. Okay. I think on a couple of bridges we may have done that, but it turns out that the characterization, through all the research at the U of I, okay, and being able to more fully characterize the energy, it's like the extra damping that you would get, or the extra energy dissipation that you would get from our quasi-isolation from our elastomeric bearings. Being able to quantify that has been very, very beneficial to us. Okay, or in the long run, it will turn out to be beneficial to us, because that's us being able to quantify the amount of isolation that we actually have and to take advantage of that. And that's almost as good. It's not quite as good necessarily, but it's almost as good as some of those other methods that you were mentioning. Okay, and it's also a lot less expensive, because it's really just building the bridges the way that we've always built them, and just taking advantage of our behavior taking advantage of the behavior of those bridges through design because we have better knowledge. Does that answer your question?
Yeah, it's answered a little bit. Yeah, I'm talking about the one high damping material because you are using some Dura 55, 60, right, for damper. Instead of this, we can, if you can use high damping, does it beneficial or not required in Illinois?
You mean to increase the You mean methods to increase the damping?
No, I'm talking about using high damping material.
High damping, I'm not sure I really understand what your question is.
High damping means when you use the material with high damping, it reduces the energy from the seismic effect.
Yeah, well, I don't think we're very sophisticated in doing that.
Okay.
I mean, I don't know, how much do you know about, are you well schooled in how to calculate or estimate damping in structures?
Yeah, we can calculate based on the hysteric loop of the cup during earthquake and how much is the area within the.
Yeah, we don't, designers generally, I'm just going to say this, generally speaking, okay, that type of characterization is not done in design, okay, especially for very, very typical type bridges, very common bridges, okay? So it is well known, it is the amount of damping that is assumed in structures when we're doing the design is only like 5 or 10%, I think. But it is well known that the damping, generally speaking, is probably a lot more than what is assumed for in design. But generally speaking, only unless you have a very complex and expensive bridge would we use those type of techniques to do those estimates of what the true damping is. Does that answer your question a little better?
Answer, yeah, a little bit. Thank you very much. Yeah.
Okay.
Is there any other question? I think that's it. Thank you so much, Dan, for this presentation. We really enjoyed it.
May I ask a quick question?
Yeah, sure.
Sorry. Yes, I've been looking around at the policies in several of the states on MSE abutments and earthquake-prone areas. There are some limitations that I've seen in Washington State and California to develop these. What is the current policy over in Illinois for doing that?
You know, I don't know if we have. I'd have to ask somebody if we've even considered earthquake loadings for MSE abutments. My guess is we probably have looked at it, but maybe not gotten really sophisticated about it. I know the person in Washington State. His name is Tony Allen. He's a very sophisticated geotechnical engineer, and he was actually the guy. He was actually the guy that was very instrumental in writing the geotechnical part of the astroseismic guide specifications. And so it wouldn't surprise me if he had a lot of input into that, along with some of his friends in California, and they would really be considering that a lot more than Illinois would. Now, Illinois does have some very sophisticated methods for dealing with things like liquefaction and things like that. We actually do have some pretty good methods for that have been developed over the years. But as far as really specifically getting into deep criteria for how to deal with MSE type abutments, my guess is that we have thought about it, but I don't know if we really have any policies or methods that are implemented that are as sophisticated as Washington State or California at this time. However, that may be coming in the next several years. It wouldn't surprise me. Does that answer your question?
Yes, thank you. But what is the name of the fellow you mentioned at Washington State?
His name is Tony Allen.
Tony Allen. Okay.
Yeah, he's very prominent. In my circles, in my bridge engineering circles, he's a very prominent geotechnical engineer who works for Washington State.
When I read the specs, the design memo from Washington DOT, they are limiting MSE abutment bridges to a maximum of one span, 3 meter, 4 meter high abutments, stuff like that. So apparently there's a, well, that was 3 years ago, so I don't know if they've updated it, but there's a limit on what you can do with these types of bridges.
That doesn't surprise me. I think they're for, you know, so in seismic design, you know, my area of expertise, I guess you would say, is more like the structural design. And I know some fair amount about soils and soil coefficients and things like that. But when you start getting into the real nitty gritty of seismic geotechnical, that kind of starts getting out of my area of expertise. However, that being said, it doesn't surprise me in the least that what I think that they're concerned about this, and they're probably worried about that reinforced soil mass losing serious strength capabilities during an earthquake. They're probably worried. It's almost like, you know how those MSE wells, they rely on what's called that reinforced soil mass. Do you know what I'm talking about?
Yes, yes.
Yeah, they're probably worried about that seriously degrading during a design earthquake. But again, that's not really my area of expertise, but my best educated guess is that they're very concerned about that.
Thank you.
You're quite welcome.
I think that's it. Is there any other questions? So there is no more question, Dan. Thank you for your time.
Hey, I really appreciate you guys inviting me, and I hope you at least found this, even though it was kind of quick, hopefully you guys found it was interesting.
Yeah, we did. Thank you so much.
Great. You guys have a great rest of your day, and I appreciate your kind attention.
You too. Thank you for your time.
Thank you.